Hello, welcome to lecture 4 of the course. In lecture 3, we solved some problems based on our learning in lecture 1 and lecture 2. In lecture 2, we have learned about the geometrical representation of the quantum state of a two-level system. And till now, we are dealing a generic two-level atomic system or two-state quantum system. In this lecture, we are going to discuss a specific case where the two-level atom is going to interact with an electromagnetic wave, say a light field. And we are going to treat this light field classically, while anyway we are treating the atom quantum mechanically. So this approach is known as the semi-classical approach, and this is the domain of semi-classical quantum optics. So let us begin our discussion. Consider a two-level atom having ground state represented by Kz and the excited state represented by Ke, and a monochromatic light field is incident on the atom, and the electric field of the light field is represented as E of t, and where E of t is given by this expression eta cap. It is the polarization of the light field. E0, that's the amplitude of the light field, and cos omega t, where omega is the angular frequency of the light field. Here we are ignoring the spatial dependence of the field and writing the field at the location of the atom. Say atom is located at, we assume that the atom is located at, say, z is equal to 0. We assume that the wavelength of the field is much larger compared to the size of the atom. Suppose this is the atom size and this is the field. As you can see, the wavelength of the field is much larger than the size of the atom, so that we can neglect the variation of the field over the extent of the atom, and this approximation is known as the long wavelength approximation. Long wavelength approximation. And this approximation is quite good as long as we are dealing radiation in the optical domain. Now the say resonant frequency of the atom is omega 0. That means this ground state and the excited state are the energy difference between them in terms of the frequency is, say, omega 0. So omega 0 is the resonant frequency, and the field frequency is different from the resonant frequency by an amount delta. Say this is the field frequency omega, light field frequency, and this difference is, say, delta, and this parameter delta is known as the detuning parameter and defined as delta is equal to omega minus omega 0. This is the so-called detuning parameter, a very useful parameter in quantum optics. It's called the detuning parameter. Now the Hamiltonian of the atom without the light field, or that means without any interaction, already we know how to write the Hamiltonian for this two-level atom. Say its excited state energy is, say, E1 and the ground state energy is, say, E0. Then I can write down the Hamiltonian in the basis state of Kg and Ke. The Hamiltonian of this two-level atom when it is not interacting with any external field, here in our case the light field, we can write the Hamiltonian as E0 Kg bra Z. E0 is the ground state energy and E1 is the excited state energy. We have Kt bra E. Now without any loss of generality, without any loss of generality, we can consider the ground state energy to be 0 and excited state energy in that case in terms of frequency, angular frequency, we can write it as h cross omega 0, right? And then this Hamiltonian for the bare atom or the isolated atom, when it is not interacting with the any field, we can write the Hamiltonian as h cross omega 0 kate E bra E. So this is the Hamiltonian of the two-level atom when it is not interacting with the light field. Now, if it interacts with the light field, this light field is basically going to induce a dipole moment, or if the atom already is having some dipole moment, then the atom field interaction is going to be given by this particular term. So let me write that the atom field interaction is given by this part. Atom field Hamiltonian is going to be because of the dipole moment of the atom. Now dipole moment, this is a quantum mechanical object because it is associated with the atom, so I am writing this operator sign here, and the electric field of the light field, I am writing it as E, which is basically the classical field. Okay, so that's the reason we are actually discussing quantum optics at this moment in the so-called semi-classical domain. And this dipole moment of the atom, in I can write it as, if I consider the atom to have only one electron, it would be charge is minus E, and the position of the electron or the location of the electron in the atom is denoted by this position vector Re. Then this is the dipole moment operator. This is basically the Re is the position operator of the electron associated with the electron, and in the basis state kg kate E, we can then express this dipole moment operator like this. As you have seen from the previous class, that this particular operator, any operator, I can write it in this particular form: I mu j kate I bra j, and here I and j can take kg or kt. So therefore, if I expand this into the basis states, then I have z mu z kg bra z plus e mu e kate E bra E, and then the other terms, say z mu e kate E, or rather I write here first kate z bra E plus e mu z kate E bra z. So I am now completed the expansion here. However, you should note one thing, that these terms, say z mu z, these matrix elements is equal to 0, and similarly this matrix element E mu E is equal to 0, because kg and kt have a definite parity, and mu has this dipole operator mu, which is minus ERE, has odd parity, and kg and kate, these states have a definite parity. Because of this reason, we can show that these matrix elements are 0. Let me explain it a little bit more clearly. Let me pick up this particular matrix element z mu z. Okay, rather let me write it the wave function form. If I write it the corresponding wave function form, then k bra z is going to be represented by this wave function psi star z. Let me consider just one dimension for simplicity. This is what I will have: mu is equal to minus ex, and kg would be psi of zx. Okay, let's say this wave function, ground state wave function, has a even parity. So psi of z of x is going to be equal to psi of z minus x, and psi star z of x is going to be equal to psi star z minus x. So it has basically even parity, and or you can also consider the case of odd parity also. Then you can show, and in fact it is quite easy to see, that psi star z x minus ex psi z x as a whole, this whole thing which is inside this integrand is a odd function. It's an odd function. Now you are taking the integral from minus infinity to plus infinity, and you know that when you are integrating over a odd function, then this is going to give you 0. So f of x here, if it is an odd function, okay, and you can show the same result even if, say, psi of z of x is has odd parity, not say even parity. Even in that case also it would turn out that this particular function is a odd function, and therefore the integrand is going to become 0, and thereby hence we see that this particular matrix element z mu z is equal to 0. And similarly, you can, by the same argument, you can also show that this particular matrix element is also equal to 0, and therefore this dipole moment operator, we can now write only two terms will be left out, and those would be z mu e k z bra e, and the complex conjugate e mu z ket e bra z. Alright, and often what happens is that we can consider this particular quantity, this matrix element can be taken to be a real quantity, and in that case I can write it like this, and this can be always done by choosing the phase appropriately. And also we can introduce an operator called the atomic lowering operator. Atomic lowering operator denoted by sigma. So let us define this quantity. Define atomic operator, lowering operator sigma. So it would be kg bra e. This is an operator. As you can see, if this operator operates on some state, then it is going to take it to the ground state. That's the reason it is called the atomic lowering operator. And the corresponding atomic raising operator would be sigma. Don't confuse it with the Pauli matrix, by the way. It is not Pauli matrix. It is an atomic lowering operator sigma and the atomic raising operator sigma plus sigma dagger. So it is ket e bra e. Ket e bra z. So this is what we define, and in terms of this atomic dipole moment operator, I can now write it as z mu e, and we'll have sigma plus sigma dagger. Okay, this is an important expression. So therefore we can write the full Hamiltonian of the atom field system like this. The full Hamiltonian for the atom field system is, you see, most of the time I am not going to write this cap sign here. Just you understand that we are talking about operator. So H is the total Hamiltonian for the atom field composite system, and it has this bare Hamiltonian without the interaction with the light field, and then this interaction term is there, atom field interaction term is there. And I can now, we have already seen that H0 is H cross omega 0 kt bra e, because the ground state energy is taken to be 0, and the atom field Hamiltonian part is this mu dot e. Okay, and this we have already seen. We have already worked out this dipole moment operator. So the total Hamiltonian, I can also write it in this form: S cross omega 0 sigma dagger sigma which you can actually show that sigma dagger sigma is nothing but ket e bra e, and the other part is minus z mu e dot e, and we also have this sigma plus sigma dagger. So this is the full Hamiltonian of the atom field composite system. Now, you see, from elementary quantum mechanics, we know that the time evolution of a quantum mechanical operator is given by the so-called Heisenberg equation of motion. So, time evolution of an operator, say A, is given by Heisenberg equation. And the Heisenberg equation goes like this: I h cross delta A delta t, the time evolution of this operator A, is equal to commutation between the operator and its Hamiltonian of the system. Okay, so this equation, Heisenberg equation, is extremely important, and we are going to apply it now to see how this atomic lowering operator sigma evolves with time. For example, let us see that just apply this Heisenberg equation to atomic lowering operator I h cross d sigma dt. This shows how this atomic lowering operator is evolving with time, and this would be sigma h. For the moment, let us consider only the bare atom, that means without the interaction, say the light field is not present. Then I can see how this atomic lowering operator is evolving in time, and h naught is sigma dagger sigma h cross omega 0, as you can see from here, right? This is the part I'm talking about, so I'm putting it here, and this I can write it as sigma dagger sigma h cross omega 0. Now it is very trivial to show that sigma dagger is equal to 1, so therefore I am going to be left out with I s cross d sigma dt is equal to h cross omega 0 sigma, and from here I can very easily see that sigma evolves in time as e to the power minus I omega 0 t, and similarly you can see that sigma dagger is going to evolve as e to the power plus I omega 0 t. Okay, so this clearly gives you an idea how this atomic lowering operator and the atomic raising operator is evolving with time. Now note that the electric field that we have written for the light field, E of t is equal to eta, that's the polarization of the electric field, E0 is the amplitude, cos omega t, where omega is the light field frequency. This I can write in this form as well: eta E0 by 2 e to the power I omega t plus e to the power minus I omega t. This one I can also express as eta E minus plus E plus, where E minus represent that part of the electric field which oscillates at frequency, actual negative frequency part. Okay, let me write explicitly: E minus is equal to E0 by 2 e to the power I omega t. This actually what I say by why E minus is put there, because this basically represents that part of the electric field which oscillates at negative frequency, minus omega t. And E plus, this decomposition is many times useful in quantum optics and in other areas. And E plus is E0 by 2 e to the power, that's the positive frequency part, e to the power minus I omega t. Here I just write it as E0 by 2 e to the power minus I plus omega t. So E plus represents the positive frequency part of the electric field, and E minus represents the negative frequency part of the light field. Okay, and this decomposition you will soon see is very useful. Similar way, we can write decompose this dipole moment operator to positive frequency and negative frequency part, because this dipole moment operator, as we have already written, it is Z mu E, and I have sigma plus sigma dagger, and this I can write it as mu plus and mu minus. And here mu plus, let me write it explicitly, mu plus represent that part who is has this sigma part, and mu minus represents that part which has sigma dagger. And as you have already seen, that sigma varies as e to the power minus I omega 0 t with time, and sigma dagger varies as e to the power plus I omega 0 t. Now I think you can see the logic why we are writing mu superscript plus and why we are writing mu superscript minus. Okay, so one part has positive frequency, then other one is having negative frequency. Now this is going to help us to write the atom field Hamiltonian in this form. So we have this atom field Hamiltonian interaction part as this mu dot E, and here now let me write mu as mu plus plus mu minus, and this electric field part, let me write it as E plus and E minus. Okay, so we are going to have four terms, four combinations. So let us look at all these combinations one by one. So let me just write first of all the combination. We have this combination mu plus E plus mu plus E minus. Mu is the operator, by the way. This is a quantum mechanical part, and E is the electric field, which is the classical part. And I have also mu minus E plus and mu minus dot E minus. Now if I look at the time dependent part for all these combinations, then you will see that mu plus E plus varies with time as e to the power minus I omega plus omega 0 t, and mu plus E minus is going to vary as e to the power minus I omega minus omega 0 t, and you will have mu minus E plus is going to vary as plus I omega minus omega 0 t, and the last one mu minus E minus is going to vary as plus I omega plus omega 0 t. Now as you can see from all these terms, out of all these four terms, the term that is mu plus E plus, that is oscillating with frequency omega plus omega 0, which is extremely highly oscillating part. It is oscillating very highly with frequency. And then mu minus E minus is also oscillating at very high frequency. On the other hand, these two terms mu plus E minus and mu minus E plus, these two terms are oscillating very slowly, and therefore what we can do is that we can neglect these two terms mu plus E plus and mu minus E minus, because they are oscillating very highly, and on the average their contribution is going to be 0, and we can neglect a highly oscillating term, neglecting a highly oscillating term, and this approximation is known as the rotating wave approximation, neglecting the highly oscillating terms under the so-called rotating wave approximation. In fact, this is called the rotating wave approximation or RWA. So this is called RWA or rotating wave approximation, one of the most useful approximation frequently used in quantum optics. And under this rotating wave approximation, Now I can write down my atom field interaction part of the Hamiltonian. HAF is equal to minus mu plus dot E minus mu minus dot E plus. And this further I can write as the full term. Let me write. I can have minus eta cap by 2 dot E0 z mu E, and then I also have sigma e to the power I omega t plus sigma dagger e to the power minus I omega t. Okay, and this I can write in a shorthand notation by this h cross omega by 2 sigma e to the power I omega t plus sigma dagger e to the power minus I omega t. So this is my atom field Hamiltonian under the so-called rotating, after applying the so-called rotating wave approximation. Okay, and here this omega is equal to minus this matrix element z eta dot mu. By the way, eta is associated the classical field, and this is the unit vector polarization direction, and mu is the quantum mechanical operator, dipole moment operator E. So this is what I have divided by h cross into E0. As you can see, this omega is associated with the amplitude of the electric field or the intensity of the electric field, and this quantity omega is popularly known as the so-called Rabi frequency, and this is a very useful parameter. It is basically associated with the electric field intensity of the light field as well as of the dipole moment of the atom, and therefore it's basically refers to when omega, capital omega, the Rabi frequency is non-zero, we can say that there is a coupling between the atom and the field. And using in terms of this Rabi frequency, the total Hamiltonian that we have is now h is equal to h cross omega 0 ket e bra e plus h cross omega by 2 sigma e to the power I omega t plus sigma dagger e to the power minus I omega t. So this Hamiltonian is what we are going to analyze further. And to do that, let us write down the Schrodinger equation describing the evolution of the atomic state. And the Schrodinger equation is I s cross delta k psi delta t is equal to h k psi, where this k psi is the represents the state of the atom, that is written in terms of the basis state kg and ke as follows, where Cg is the amplitude associated with the ground state probability amplitude, and C is the probability amplitude associated with the excited state. Now, using this state vector in the Schrodinger equation, we can easily obtain the following coupled differential equation. And in fact, we are going to solve some problems in the problem solving session in 2. There are many of the mathematics that I'm going to skip in these lectures. Maybe I'm going to address it there, or you can easily fill up the gaps yourself also. It's very easy to get this set of couple differential equation. Very easily you can get this couple differential equation. Let me write them. You will have delta Cg delta t is equal to minus I omega by 2 Ce e to the power I omega t, and delta Ce delta t is equal to minus I omega 0 Ce minus I omega by 2 Cz e to the power minus I omega t. These are the coupled differential equation which associate the probability amplitude of the ground state and the excited state. And As you can see, this couple equations involve oscillating terms at optical frequencies via this term e to the power I omega t and e to the power minus I omega t here. Many a times it is convenient to get rid of these highly oscillating terms, and this can be done by going over to a rotating frame of the laser field by defining the slowly varying excited state amplitude as Ce tilde, and this is related to the excited state amplitude Ce as Ce tilde is equal to Ce e to the power I omega t, and Cz tilde is equal to Cz, because already we have taken the ground state energy to be zero without losing any generality, and using this transformation we can rewrite the equation of motion as follows. It's very simple to get this set of coupled differential equation in this rotating frame of reference of the laser field. It is Cz delta t is equal to I omega by 2 Ce tilde, and delta Ce tilde delta t is equal to I delta Ce tilde minus I omega by 2 Cz. I urge you to work it out yourself. It's very simple. You just have to use this transformation in this equation, and then you will be able to get this set of couple differential equations. Now let me talk a little bit more about unitary transformation. As you have seen that here we are going to the laser field frame, and this is equivalent to saying that we have, mathematically speaking, we have basically applied the so-called unitary transformation, and unitary transformation is very fundamental to quantum optics, and in many places, even in quantum mechanics, unitary transformation is frequently used. Basically what we are doing here is that we are going from the state vector k psi to a new state psi tilde, k psi tilde, induced by unitary transformation u. That means I am going to a new state vector from the old state vector k psi by applying this unitary transformation or the unitary operator here, and both this k psi tilde and k psi is has to obey the so-called Schrodinger equation. I have the Schrodinger equation for k psi as this. This is equal to h psi, and the new state vector psi tilde is also has to obey the Schrodinger equation, but in the process the Hamiltonian is now changing from h to h tilde, and so this is the Schrodinger equation. These equations has to be obeyed, and it is easy to show that h tilde, the new Hamiltonian, and h are actually connected and related. You can show it very easily. Let me leave it as a problem to you. You can show that h and h tilde are related by this particular expression. H tilde is equal to, you can show it very easily by dint of these equations, because both psi and psi tilde has to obey the Schrodinger equation. Then just by simple mathematical manipulation you can show that h tilde and h are related to each other by this expression. Here h tilde is equal to u h u dagger plus I h cross delta u delta t u dagger. Please show this expression. Otherwise, anyway, we are going to do it in our problem solving session number 2. Now, coming back to our two-level atom interacting with the classical light field, we can show by using this relation that h tilde, our new Hamiltonian in the rotating frame of reference, is simply h tilde is equal to minus h cross delta kate e bra e plus h cross omega by 2 sigma plus sigma dagger. Now you see we are now getting rid of the time dependence term here. Let me stop here for today. We are going to continue our discussion in the next lecture. So see you in the next lecture. Thank you.